Okay, that's running. So what we're going to do today is we extend the Lagrangian formalism right into the Hamiltonian formalism. Now you guys may have already heard about Hamiltonians in some class or other. Is that the case? 102? Are you saying 102? Have you heard of Hamiltonian?
Hamiltonian
Has been, okay, good, good. All better, all better. So let's go ahead and title this Hamiltonian mechanics. It's an extension of what we've been doing. Just another layer deeper into the formalism. But I'll just start with this. So we have the Lagrange formalism, and we need a Lagrangian of Q dot and T. Okay. And this represents the collection of coordinates. This represents the collection of their time derivatives, the velocities of this time. What we're going to get with Hamilton's method, instead of the Lagrangian, we're going to construct something called the Hamiltonian. And there it's going to be a collection of coordinates. They could be the very same ones as above. A collection of momenta and the time. And what links these two is that the piece of I is defined as dl dq sub I dot. Right, so we've taken these derivatives before, and they are referred to as the generalized momentum. Right? Generalized momentum. So it turns out it can be very useful to express your problem in terms of coordinates and momenta in time instead of coordinates and velocities in time. And I'll show you the reasons for that in a moment. So yeah, to actually study Hamiltonian mechanics, you have to start with Lagrangian mechanics. You can't start with this theory, you actually have to start here and then move on to that. So this is a good review of some of the things that we've been doing. And here, we know the equations of motion, generalized momentum, and then we can write d over dt, gl, dqi dot, minus partial qi equals 0, right? So those are the equations of motion, and we have some other tricks up our sleeve as well. With Hamiltonian mechanics, this thing here is the energy, and for the moment I'll just write it's the energy T plus U. Remember, this thing is the T minus U. And then the question is, what are the equations of motion going to be? What are the corresponding equations of motion? So that's our task, is to figure that out. Equations of motion. Question mark. So it looks like it's just another layer of formalism, but we'll see what comes out. And it's not just a layer of formalism, it's fundamental if you study quantum mechanics, for example. The Hamiltonian formalism. So yeah, you have to go through this and this. And so here's what we'll do. What we're going to do next is figure out the answer to this question. What are the corresponding equations of motion? That was the actual definition of the energy in Lagrangian mechanics. And if you had a normal or standard Lagrangian, it turned into T plus U. Okay, but this was its original definition. This was the quantity that was conserved if L does not explicitly depend on time. So now I need some more board, so I'm going to erase this. And I'm going to form a complete differential of this. Because I'm going to impose this condition. This is what I want Hamiltonian to be the energy. I'm going to do a complete differential of this thing. And that would be the sum over. Oh, actually, let's do this. Let's do this. So we're going to have this, H equals E. We're going to arrive at, we're going to say sum of Pi Qi dot minus L of Q1 to Qn, Q1 dot to Qn dot and P. So that's something we can actually work with. I want to put it in the form we can work with. And I'm going to take this H. So here we go. So I would have, think of product rule. I would have dPi times Qi dot plus Pi times dQi dot. And then from the Lagrangian here, I would have sum over dL dQi, and I have a sum of partial L Qi dot, dQi dot. And then outside of both of those summations, I would even have the minus dL dt dt. Good, barely fit it in there. Okay, so that's taking a total differential.
Shouldn't there be a minus sign?
Here.
Yeah.
Yeah, thanks. Minus from there, down. Good, so we'll put a red box around this guy. So this is what we're after. If we already had, for H equals H of Q1 to Qn, P1 to Pn, and T, that's comma. For this situation, we would also have a dH. So this is the result we're looking for, and we'll have dH with the partial H, partial Qi, dQi, and then for the second set, we'd have partial H, partial Pi, dPi, and finally, outside of the sums, we would have dH, dt, dP. So the top box is how we're going to construct the Hamiltonian, and the bottom box is what the actual Hamiltonian would deliver. And that means we have to match these top and bottom expressions. We have to match them up and see what we have. So we have, by the way, this is under that sum. Make sure that's under that sum there. Okay. If we're matching these up, one of them would just easily get, apparently this dH dt will equal minus dL dt. So we'll have dH partial equal to minus DL dt. What else do we have here? We have dH dqi which is right here, is minus dL dqi dot okay, but dL dqi dot hold on. Hold on here. Let's strike some of these first. I gotta strike a couple right here first. Yeah. So dL dqi dot is p sub I, so p sub I dqi dot, p sub I dqi dot. These two go away. And that leaves dpi qi dot, dpi qi dot. So good. So this one gives me qi dot equals ph pi. So I'll circle those. And then and then this one here, sorry about that, I'm going to return to this one here. Okay, so this one here, I'll do a wiggly underline. I can get dH dqi. I get minus dL dqi. But this is equal to minus d over dt dL dqi dot from the Euler-Lagrange equation. Euler-Lagrange. And dL dqi dot is pi, so that's negative pi dot. So that's the collection of these three results that I get from matching these two. This one, and I'm going to rewrite them in a moment. But yeah, I matched coefficients. And these will actually be the differential equations of Hamiltonian mechanics. So yeah, once again, before I erase this thing here, you form these two total differentials, and then you have to recognize things that cancel. You have to recognize, in this last one here, you have to recognize that this negative dL dqi is negative d over dt dl dqi dot. That's the Euler-Lagrange equation, and because that is the generalized momentum, that's pi dot. Good, so now I'm gonna erase this and write these things out. And then we'll do the steps that we have to follow to make sense of this. This is similar to the Lagrange formalism in the sense that eventually you'll see it enough to just know it. I mean, you'll memorize these basic things here. So to construct Hamiltonian and the equations. It's actually all been on the board now. So the first step we do is we need the set of coordinates. Oh, sorry, qi, the set of qi dot and L, already short of q dot, and t. So the first step is we just have to do what we always do in Lagrange mechanics. Figure out the Lagrange. That's what we're saying right here. And we have to know that p sub I is equal dl dqi dot. So this is always just a repetition of the Lagrangian method. But the next thing is we write down E equals sum over dl dqi dot minus L. And the third step, because remember, this was our proto-Hamiltonian, this was our energy. We have to convert this to the Hamiltonian. It's really an algebraic problem. We have to, see, these are already p sub i's, right? We have to just express energy, so express E equals H of Q, P, and T. So that's sort of an algebraic task. Sometimes easy, sometimes not so easy. And as soon as we get this, we'll run through an example. And then for the equations of motion now, so this is what we all came for, equations of motion that we just found over here. They are qi dot is partial h with respect to pi, and pi time derivative is minus partial h with respect to qi. These are called the canonical equations because they look so good. It has nothing to do with religion. Okay? Canonical equations, Hamilton's equations, and then this one here, dh dp equals minus partial L with respect to time. So there's something that is striking about this construction. How many equations are there? This is n equations, right? I equals 1 to n. This is also n equations. I equals 1 to n. And this one is actually not a new differential equation. It's just kind of a relation between the two objects here. What has happened here, make those dots a little more profound. What's happened is that we went from a system with n second order equations to a system with 2n first order equations. Twice as many differential equations, but they're lower order. They're good or bad? Who's to say, right? Half-half. Twice as many equations, not good. First order equation is good.
One begins to see why people invented computers.
Yeah. I know, n is anything greater than 2, then you got problems. Unless you're just doing theoretical calculations. After all, our mass is on a chain, n was very large, and we knocked it out, right? But yeah, so those are the canonical equations, and this is the process to keep in mind. The proof of this was this process right here. So this is a way of getting new, transforming to a different system. By the way, this is called the Legendre transformation. This thing here, if you're able to go from here to here, it's a Legendre transformation. So it's used in other places. In thermo, you see it a fair amount. But so let me show you guys just the simplest example that sense, kinetic and kinetic. In fact, I have a great problem with that. I may save it for the final one. Yeah, so yeah, there are, his question was, are there conditions where the Hamiltonian equals the Lagrangian? And if you have a free particle, the Lagrangian and the Hamiltonian, the energy, they all have the same value, right? But you have to be aware that you have, of which differential equations you're using. So anyway, let's make sure we see this really basic example. And that is a free part, not a free particle, that's too basic. A one-dimensional system. So you could say, we'll just start with L as a half m x dot squared minus u of x. Okay? Your basic one-dimensional system. Simplest one. Good. So the energy, and actually P is equal to dl dx dot is mx dot. Definitely good to review all these things, right? The generalized momentum is simply your linear momentum. Mx dot. Now we form the energy. So this is one. Okay? Now for part two, we form the energy dl dx dot x dot down there. And that's mx dot minus half of x. Now we're just going to write this down very meticulously. That's mx dot squared minus a half, same, so that's a half mx dot squared, negative is positive, plus u of x. So this energy, I'll put a box around it. It's not quite yet the Hamiltonian. It's the energy, but I have to express it in this form here. So my third step, I'm just paralleling everything we've got there, is that H is going to be equal to 1/2 m, and this x dot is P over m. So this is where it happens. P over m squared plus u of x. And I'll bring this down to here so we can check it out. So we've got h of q and p squared divided by 2m plus u of q. So there's our Hamiltonian. And you'll notice this one didn't have a time dependence explicitly. This one doesn't either. And so this is trivially fulfilled. Right? Trivially fulfilled. Okay, who wants to try the equations of motion? The box and then right here. They're important. Don't reach the room if you could. So what about the equations of motion? Now we go back to these. Q dot, this is a subscript I, so Q dot equals dH dP. Take the derivative with respect to P here, we just get P over M. And, Q dot, I should have said X dot. Okay, let's go ahead and call this X, so as not to change things too much. Okay. So the X dot, which is the Q dot, so the X dot equals P over M, and that was going to get a check mark. So that's true. What about P dot? P dot's the one that gets the minus sign. And it's going to be minus dH dx. Q, so it's got the minus sign h dx, so that's du dx. What do you guys think about this equation? Newton's law, right? Newton's law minus the minus the gradient or minus the derivative of the potential. So this is no more than and no less than what the Lagrangian equations give us. Okay, it's exactly the same thing. So we just come full circle, and you could justifiably ask at this point, why did we even do this? You guys wouldn't ask such a question, would you? But it's a convincer that we came full circle, everything pans out. So the reason we do this is because we have other things up our sleeve. Okay? But this little calculation just shows you that it all works out. Good, so what's our next example? You know what, I'll go ahead and leave the whole recipe here on the left side. Here I've got an idea, I've never done this one, but I'll add this to the homework. This week or next week, who's to say? It's actually a good one. How about the inverted cycloid? Where we had x equals r theta minus r sine theta, y equals minus r minus r, no, inverted cycloids, it's going to be minus 2r. Plus r cos theta. But that equals pi minus 2r, yeah, that's good. And you guys remember we had the Lagrangian for this thing, did we not? That's in our notes somewhere. Do the homework problem. I'm going to go ahead and write it out. We had something like 2m 1 minus cos theta theta dot squared minus m g, and then this y here, I could do r cos theta minus r. So we never actually wrote the equations of motion out for this thing. Might be a good idea to do that sometime. And because we looked at the small oscillations. It's a nice small oscillation problem. But it actually also has full equations of motion. And what we want to do is construct the Hamiltonian for this problem. So that would be h of theta and piece of theta. Right? This thing here is L of theta and theta dot. So h of theta and piece of theta, right, this piece of theta, EL theta dot. So you construct h of that, so it's a little more involved, but it's no big deal, no big problem. And write out the equations of motion. And you know what, I'll say for this one as well. Write out the equations of motion. The equations of motion. They take the form that you can't actually solve. Okay, they're very difficult to solve. Again, you you could integrate it numerically, but what we did previous to this, so we're not gonna actually solve these waves more, but we can practice writing them out, okay? What we did previous to this was we just talked about the behavior needed to small oscillations. That's easy to do, but if you actually write this whole thing out and take the greatest motion, bit of a mess, but it could be worse. So yeah, I'll call this a homework problem. We can put that on next week. Next week or so, after the exam. So we're going to continue in this vein with one or two more little examples. They keep leaving the list up on the left side. So yeah, this is a good, still a one-dimensional problem. Okay? One-dimensional problems can cause you that problem too. So the last example we're going to do is the plane polar coordinates. Okay? So we work with those sufficiently, and I'll probably assign that as well, or I'll get started with it. Continuing with the examples for the Hamilton's method. Plane polar coordinates. And this one we can just knock out, right? Yeah, so plane polar coordinates is half m r dot squared, r squared, v dot squared, minus u of r and phi. And we know if r is constant, we can talk about a simple pendulum, and if u is independent of v, we have a separate force problem. So this one we've actually done much work with already. So what's the Hamiltonian for this thing? I'm going to slightly cut to the chase. In all of these that have the standard form, the energy really is just the potential plus kinetic plus potential. So we can make a little bit shorter work of this. Half m r squared v dot squared plus u of r and phi. But that's not yet the Hamiltonian. So remember, we need to get the piece of r. Right, what I'm calling here piece of I. In this case, I have r and phi. So I'm going to call piece of r is dl dr dot. And we go back here, we have mr dot. And piece of phi is dl d phi dot equals mr squared phi dot. What we call the piece of phi before. Who recognizes this thing? What is this? What was its physical meaning? It's the angular momentum. So this is the radial momentum, and this is the angular momentum. That's what it means to be a generalized momentum. Piece of phi. And so what we now do is make the substitution into here, and our Hamilton function will be a half m piece of r over m quantity squared plus a half m r squared. The phi dot is piece of phi over mr squared has to be squared plus u of r and phi. And this will simplify one more time. Oh, wait. So this one, similar to what we just had before, piece of r squared 2m Well, yeah, anytime you write these out, best off repeating the construction, knock out the equations. They're, of course, in this form. How many are there for this system now? How many Hamilton equations? 4, right? There's gonna be 2 for piece of R and piece of B, and 2 for R and B. You'll have 4 equations. Let's see. Yeah, before we do this stuff formally, I'm actually going to discuss this thing a little bit more. Suppose you were not a function of phi. U's not a function of phi. What we're going to find, the same as the Raunchy mechanics had, then this is going to be a constant, and then this will look just like our central force problem. This will actually be the effective potential we had last semester. So when we did this business with the effective potential, in essence, we were, heading towards Hamilton's method right there. But that has to be taken systematically. Although, there's a couple of things to do here, but I've got a minute. Let me finish up with the following situation. So now that we've seen this and I've mentioned it, I will, and this will be, this is kind of what we'll start with next time. So suppose we have this Hamilton method, 1 through 4. So I'll call this 0.5 of Hamilton method, referring to this construction here. If H is not explicitly a function of some Q sub K, that's how I express that, right? It's not explicitly a function of Q sub K, then P sub K, P sub K dot minus DH dQ sub K is of course just a 0, right? No explicit dependence, partial is equal to 0. And what do we have? Conservation of this quantity here. So then P sub K is constant. So what I'm talking about is 0.5 of the method is cyclic coordinates. And all the advantages that we have in Lagrangian mechanics we inherit for Hamiltonian mechanics. All the advantages of having a cyclic coordinate. And it also remains our primary goal. We just want to find a coordinate system with the most cyclic coordinates in order to solve problems. Okay, good. That's all I've got for you today. So Friday, come prepared with any questions and presentations that you can come up with for all the wave stuff. And anything else as well. Okay.